Welcome to Lecture 4.4, Invariant Subspaces. We will continue our assumption that X is an n-dimensional vector space over an algebraically closed field K. Let's begin with defining the term that's in the title. An invariant subspace of a linear map A from X to itself is any subspace Y for which A of Y is contained in Y itself. Of course, it's also a subspace of Y, but the key point here is that if you start with Y and you apply A, you get back within itself. If we know A, we may refer to such a subspace as being A-invariant. Suppose now that our vector space X decomposes as a direct sum of two A-invariant subspaces. I claim that if we have a basis y1 up to yk for big Y and zk plus 1 up to zn for big Z, remember the union of these is the basis for X, then the matrix of A with respect to this basis, if we put it in this order, is block diagonal. This is easy to see. If we write our basis vertically like we normally do, y1 up to yk, zk plus 1 down to Zn. Remember what we do? We apply A to each of these vectors, and then we write the image of each as a linear combination of the same basis. So A11 y1 plus, etc., all the way up to AK1 yk. But now, because these are both A invariant, A sends each yi to a linear combination of the yi's. So now we're going to get plus 0 zk plus 1 all the way up to 0 zn. And similarly, ak or ayk down here is going to be a1 k y1 plus a k yk plus, again, 0 zk plus 1 all the way up to 0 zn. And then similarly down here, since z is A invariant, A is going to map each of these zi's to some linear combination of themselves. So we're going to get a zk plus 1 is 0 y1 plus 0 yk plus some a k plus 1 k plus 1 z k plus 1 plus a n k plus 1. Hard to keep track of these indices, zn. Remember that the rows here are the actual columns of the matrix, so it's doubly confusing. So finally, the last line is also going to be 0 y1 plus 0 yk plus a k plus 1 n z k plus 1. Details really aren't that really important. A n n z n. So the main point is that the only non-zero entries are in these two blocks. So we have one block here, another block here. And because these spaces are A invariant, all of these entries here and all of these entries here are going to be 0. So that's important to keep in mind. What we'll do in this lecture and in subsequent lectures is we will break up our vector space into a direct sum of so-called eigenspaces or generalized eigenspaces. And those will correspond to what you've likely heard, I think me say, or maybe elsewhere, Jordan blocks of the Jordan canonical form. Okay, so that's a bit of a preview. It is easy to see how this extends to a sum of more than two A-invariant subspaces, say y1 up to yl. Just a few moments ago, I talked about how we will be decomposing our underlying vector space into a direct sum of generalized eigenspaces for different eigenvectors, and that's in the future. But for right now, let's just focus on a single individual generalized eigenspace. Now, in the previous lecture, I defined what a generalized eigenvector is, and it's literally any vector that is in the null space of A minus lambda I to the m for some m. And here's how I like to think about that. I think about them as coming in chains. So if Vm is in the null space of A minus lambda I to the m, that means m iterations of this map will kill it or send it to 0. So Vm, if you apply A minus lambda I, gets sent to Vm minus 1, and that gets sent to Vm minus 2, and so forth. And then eventually we get the V3, which gets sent to V2, which gets sent to V1, which gets sent to 0 by A minus lambda I. So algebraically, Vm minus 1 is A minus lambda I times Vm. Vm minus 2 is A minus lambda I squared times Vm. And all the way up to V2 is what you get by applying A minus lambda I m minus 2 times. V1 is what you get by applying it m minus 1 times. And then finally, if you apply it m times, it finally sends it to 0. So it should be clear that this is invariant under the linear map A plus lambda I. Or technically what I mean by that is the span of these vectors is invariant under A minus lambda I. And actually, not only is it invariant under A minus lambda I, but it's also invariant under A. And that's easy to see. If we take, let's say, Vm, for example, and we apply A to it, we can see what that is from up here. If A minus lambda I times Vm equals Vm minus 1, then A Vm is equal to lambda Vm plus Vm minus 1, and so forth. So A times Vm minus 1 equals lambda times Vm minus 1 plus Vm minus 2. So A is going to map all of these eigenvectors to generalized eigenvectors to linear combinations of themselves. And that's an important fact because we will be coming up with a matrix of A minus lambda I and also of A. In this lecture, we will explore what happens when we have multiple genuine eigenvectors and the invariant subspaces that arise and what they look like in matrix form. In this example of these generalized eigenvectors, only one of them, V1, the first one, is an actual genuine eigenvector. All of the others are truly generalized eigenvectors and not genuine. In order to motivate some of the big ideas about generalized eigenvectors and eigenspaces and the spectral theorem in Jordan canonical form, some things that will appear over the next few lectures, I think it's very important to have a really good example to do in advance. And here's one that I really like. It's not too big and not too small. Suppose that A has characteristic polynomial t minus lambda to the 11. So it has only one eigenvalue of multiplicity 11. And suppose that it has 4 genuine eigenvectors. In other words, the dimension of A minus lambda I is 4. Now, obviously, any linear combination of these is an eigenvector, so there's infinitely many, but what I really mean when I say there's 4 eigenvectors is that there is a 4-dimensional subspace consisting only of eigenvectors. And for that particular subspace, you can imagine that if you have A times that entire, let's call the subspace Y, A times Y, then that will just equal lambda Y. So it literally takes the subspace, I can't really draw it in 4 dimensions, but it takes, and it just blows everything up, scales everything by a factor of lambda. What I will do now is show you one such possibility for the generalized eigenvectors of A. And we will start with the genuine eigenvectors. We know there are 4 of them. Let's call them V1, W1, X1, and Y1. And these things all get mapped to 0 via A minus lambda I. So now we can look for generalized eigenvectors. It may be the case that there is some V2 that gets mapped to V1, or some W1 or W2 that gets mapped to W2, and so forth. We can ask whether or not any of these things, or all of them, have some preimage under A minus lambda I. Let's suppose that 3 of them do, and 1 of them does not. Let's call these generalized eigenvectors V2, W2, and X2. We can now ask, do these things have preimages? In other words, is there a V3? Is there a W3? Is there an X3 that map onto V2, W2, and X2? Let's suppose there are just 2 of these. Suppose there's a V3 mapping onto V2 and a W3 mapping onto W2, but nothing that maps onto X2. We can keep going. Is there a preimage of V3 or W3? Once again, let's suppose that only one of these has a preimage and the other one does not. Now, if you look at this, we have 10 eigenvectors, generalized eigenvectors so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you believe me in advance that there will be a basis of generalized eigenvectors, we'll not prove that now, but for the sake of understanding this example and appreciating it, I hope that you will go along and believe it, at least temporarily. Trust me, it is true. So if there is one more generalized eigenvector, we've already established that nothing maps onto W3, X2, and Y1, so it has to map on to V4. And let's call it V5. And this is going to be one of the big ideas of this series of lectures, at least this section, is that we have 11 generalized eigenvectors and they will form a basis of X. And this is always going to work out this way. So we will prove this over the next few lectures, but I hope for the sake of this example, just understanding where we are going, you will suspend your belief and trust me that it will work out and that, yes, we will prove it. Okay, so when I say things are as nicely as this, what I mean by that is we are never going to have any branching. We're never going to have an X2 that also maps to X1. Well, that's not true. We actually will have infinitely many things that also map to R1, but we only need to pick one of these. All of the things that map to X1 are going to be equivalent modulo some space, so in some quotient. We'll explain what we mean by that later. We also need to show that these things are, in fact, linearly independent. And if we do that, then in this case, we have a basis. But in general, we need to show that we can always extend these things backwards. We're not going to never get stuck here and not be able to extend things. So there's a lot of things in here that we have to prove. But the basic idea is this is always going to work. Now, let me ask, what invariant subspaces do you see? And there's a lot of them. So first of all, there is the subspace spanned by all of these. Each row will span a subspace. So that row, the second row, this, well, I don't really need these zeros, but oh well, it doesn't hurt to include them if we're just talking about subspaces. So each of these rows will span a subspace. But there's other things. So I've already talked about how this V1, W1, X1, and Y1 is a subspace of the eigenvectors. It's a 4-dimensional subspace. And then there's others. Well, actually, let me tell you what this. So remember, this is the null space of A minus lambda I. And now what about, let me draw another subspace. I'm running out of colors. This one here. When I say this one, I mean it's the one spanned by these 7 vectors. This is the null space of A minus lambda I squared. Everything in here gets killed by, at most, 2 instances of A minus lambda I. And then similarly, I'm ready to give up with colors. This is going to be A minus lambda I. Sorry, it's the null space of A minus lambda I cubed, and so forth. And we can even mix and match. We can take v1, v2, w1, w2, w3, and y1, and that is going to be an invariant subspace because when we apply a minus lambda I, it sends everything to the right. Now, in the previous lecture, I said that any of these chains, the subspace spanned by them, is invariant under a minus lambda I, but also under A. And that's actually something that is true more generally for any subspace, and I think it's worth saying that right now. So being A invariant and A minus lambda I is invariant is the same thing. So let's suppose that A minus lambda I times Y is contained in Y. Then I claim that that means that a y is contained in y as well. And to see why, let's just take some a vector little y in big Y, and we know that a minus lambda I times little y is some, say, y prime in y. So that means that a y equals y prime plus lambda y, which is also in y. Okay, so any of these invariant subspaces here, not just these chains, but also this yellow one, this green one, this black one, etc., or a mixed bag of them. Like I said, you can mix and match. You got to be careful. You can't take v1, v2, and v5 and w2 and w1. You have to take anything that, or if you take any of these VIs, if you take any of these generalized eigenvectors, you have to take everything to the right. But all of these are invariant under a minus lambda I and also invariant under A. Okay, now that we have cleaned up all of that mess, let me define Nj to be the null space of a minus lambda I to the j. So N1, we've already talked about, is this four-dimensional subspace generated by the genuine eigenvectors. So that's going to be four-dimensional. Let me write N1 here. N2 is going to be all vectors that are killed by two iterations of a minus lambda I. So that is all of these 7 vectors, or the span of these 7 vectors. So this is going to be N2. I'm probably using different colors than I did in the previous slide, but that doesn't really matter. So N3 is going to be this 9-dimensional subspace. So let me write the dimension here. So this is 9-dimensional, this is 7-dimensional. Notice how it should be obvious that Nj is always going to be contained in Nj plus 1. So N4 is going to be this space here. This is going to be 10-dimensional. And then N5 is going to be 11-dimensional, spanned by all of these things. So this is going to be N5. This is 11-dimensional, and I forgot to write N4, which is right there. And then, of course, N6 is equal to N5 because we don't have any more generalized eigenvectors. So this is going to terminate, and all successive N7, N8, etc. are all going to be equal to N5. At this point, I want to ask you a question. See if you can figure it out. What is the minimal polynomial of A? So it's going to be t minus lambda to some power less than or equal to 11 because it has to divide the characteristic polynomial. And we also know that the minimal polynomial ma of A has to be 0. So this is a minus lambda I to whatever the heck that k is. So let me put a k here. This has to be the 0 map. This has to be 0. And what I mean by the 0 map is it has to annihilate or kill every single vector in the space. And if you believe me that these 11 vectors, generalized eigenvectors, form a basis, then it has to kill every single one of those. So how many iterations of a minus lambda I do you need to kill all 11 of these vectors? Well, you need 5 to kill V5. 4 won't do it. 4 will send it to V1. And also 5 will suffice. So I claim that the minimal polynomial of this matrix is t minus lambda to the 5. Moreover, what we will see later is that this completely characterizes the similarity of matrices. In other words, if we have two, let me not say matrix, let me say two linear maps such that their characteristic polynomials have the same multiplicity for every eigenvalue. And moreover, if you draw these chains and they look the same after shuffling, then those two linear maps are similar. And that is an if and only if. So how do you characterize that? Well, one way to characterize that, I claim, is by this sequence. Well, let's see. One way in this case to characterize that is by saying this is length 5, this is length 4, this is length 2, and this has length 1. And so these sometimes are called I think they're called invariant factors. I mean, they're the sizes of these, I call them horizontal invariant subspaces, these chains of generalized eigenvectors. These numbers are also encoded via this sequence of the dimension of n1, n2, n3, etc., etc. Now, probably the easiest way to see this is in matrix form. What this, as we will see later, what this will correspond to is that the matrix of this, with respect to this basis, is going to be 11 by 11, and I claim that it's going to be block diagonal because each of these is an invariant subspace. So it's going to have a 5 by 5 block here, 5 by 5. It's going to have a 4 by 4 block here. It's going to have a 2 by 2 block here and a 1 by just a 1 entry right there. And these are going to be Jordan matrices. I think I showed them to you before. We'll do it more again later. So where we're going with this is if we can prove that everything that I claim to be true of this picture is true, and that this determines similarity, well, if we prove this is true, and I guess we have to prove the similarity statement, then what we will eventually get to is that any two linear maps are similar if and only if they are similar to the same block diagonal matrix. We call this a Jordan matrix. And this is like a generalization of the notion of being diagonalizable. So in the case when we have no generalized eigenvectors that aren't genuine, this thing is just, we don't have anything back here, and all we have are these single length 1 chains, the eigenvectors, and we have a diagonal matrix right here. Okay, so moving on, there's several features of this diagram that we want to capture. The length of the longest chain is one of the most important ones. It tells you the exponent of the minimal polynomial. And now you can actually see why, if a matrix is diagonalizable, if and only if the minimal polynomial doesn't have any repeated roots. Because a repeated root means that there's a generalized eigenvector that's a distance more than 1 step away from 0. So the length of this longest chain, we are going to call this the index of the eigenvalue. That's also going to be the exponent of the minimal polynomial. It's also going to be the size of the largest Jordan block when we get there. So 3 different ways to characterize it: polynomials, in terms of this null space business, and also the size of the Jordan block. The number of chains is in other words the number of eigenvectors. We're going to call that the geometric multiplicity of the eigenvalue. So the standard multiplicity, 11 here, is going to be, we're going to call it the algebraic multiplicity, which is the number of generalized eigenvectors. But the geometric multiplicity is going to be the number of chains. So in terms of the Jordan canonical form, which we still haven't formally presented, the geometric multiplicity is going to be it's the number of Jordan blocks. Each block is going to correspond to a chain, and each chain has a genuine eigenvector. And then the algebraic multiplicity, in terms of polynomials, is just this exponent. In terms of eigenvectors, it's the number of generalized eigenvectors, independent ones. And in terms of the matrix, well, it's just the sum of the sizes of the Jordan blocks. And this is 11 by 11. This has one eigenvalue, but in general, if we have multiple eigenvalues, then we're going to have blocks for each of the eigenvalues. Okay, let's now define these things formally. The key idea, which we have not yet proven but will soon, which makes this whole thing work, is that for any A, there's always a basis of generalized eigenvectors. I'm calling this definition and preview. And maybe I should add the term summary too, because we talked about most of this, if not all, on the previous slide. But I think it's important to put it together in one place. I will give the formal mathematical definition of 3 key terms involving eigenvalues, and then I will give several equivalent characterizations from other points of view. The preview part is because we haven't necessarily proven everything to establish the equivalent characterizations, but nonetheless we will do so soon, and I think it's still very helpful to see these side by side. Jordan canonical form is one of these examples that we have not done yet formally, but I have dropped enough pieces of information about it that you should have a general idea as to what it is. And I also expect that some people are watching this video knowing what it is, but they want to learn more about it, especially behind the scenes. Okay, so our first definition is algebraic multiplicity of lambda. That is simply the largest k such that t minus lambda to the k is a factor of the characteristic polynomial. It is also the maximum number of linearly independent generalized lambda eigenvectors of A. Now this is new term/notation, lambda eigenvectors, but I think it's clear from the context that this is just easier than saying eigenvectors of A corresponding to lambda. Now this is one of those things that I haven't yet established. It really depends on you believing this key idea that there is always a basis of generalized eigenvectors of A. And we'll get there soon. This key idea in matrix form is just the Jordan canonical form. And that says that the algebraic multiplicity is the number of diagonal entries. So remember what that means. Every one of these generalized eigenvector chains corresponds with a Jordan block. And there's a diagonal on the entry of each of these. So the number of generalized eigenvectors is just the total number of entries in here. It's the sum of the lengths of the chains, and the length of each chain is the size of each block, which is the number of diagonal entries. So for example, if we have 2 chains like this, then we will have 2 blocks like that. And there might be others for other eigenvalues as well. So there might be one with a mu and so forth. Next is the geometric multiplicity of lambda. That, by definition, is the dimension of A minus lambda I. That has the geometric interpretation as being the maximum number of linearly independent, genuine lambda eigenvectors of A. Compare that to the algebraic multiplicity, which counted the generalized eigenvectors. This also counts the number of Jordan blocks corresponding to lambda. Remember, the number of genuine eigenvectors is like the number of chains in this picture. And each chain corresponds to a Jordan block. Finally, the index of lambda is the smallest d, such that nd equals nd plus 1. Remember what that means, that's the null space of A minus lambda I to the d is equal to the null space of A minus lambda I to the d plus 1. In terms of our chain picture, that is the length of the longest chain of generalized eigenvectors. So if we have V1 getting mapped to 0. We got v2. Remember, that goes all the way back to vm. This m is the index right here. If you believe this key idea, then the index is the largest m such that t minus lambda to the m is a factor of the minimal polynomial, because we need at least m copies of a minus lambda I to send vm to 0. And finally, that is the size of the largest Jordan block corresponding to lambda. And we'll see all of this more later. Though we won't prove that X has a basis of generalized eigenvectors in this lecture, I will show you a key technical lemma of why that works. And then I will apply it to our favorite 11 by 11 example. So I will leave the verification of this as a homework exercise. And it looks complicated, but it's really not that difficult. It's more just an exercise in notation. And I will also explain what this really means. It's not as bad as it looks. So this says that a minus lambda I, we know is well-defined, is a map on X, but I claim it's a well-defined map on the quotient space as well, if we quotient out nj plus 1 by nj. And moreover, it's 1 to 1. So formally, a minus lambda I maps nj plus 1 mod nj to nj mod nj minus 1 by sending the equivalence class of x to the equivalence class of a minus lambda I times x. One corollary of that, which is always the case anytime we have a linear map A that maps x to u, that's injective, is that the dimension of x is less than or equal to the dimension of u. You can't ever map in a one-to-one fashion and get to a smaller subspace. So one of the key takeaways from this is that the dimension of nj mod nj minus 1, which we still haven't fully dissected to understand yet, is at least as big as the dimension of nj plus 1 mod nj. Okay, let's now compare it to that 11 example so we can really start to understand what this is all about. Let's start with n5 mod n4. So this n5 is 11-dimensional. It's spanned by these 11 vectors. N4 is 10-dimensional. So the quotient is going to be 1-dimensional. And a basis for the quotient is going to be v5 bar, because v5 is something that is in n5 and not in n4. Now, n5 is the set of all vectors that are killed or annihilated by a minus lambda I to the 5, by 5 iterations of this, which is everything. Whereas n4 are the vectors that are killed by 4 iterations of a minus lambda I, which is, well, all 10 of these, but not v5. So an element that's in the quotient is going to be an equivalence class, but the individual elements in the equivalence classes are I guess in the non-zero equivalence classes are those things that are killed by 5 elements. So v5 is killed by, needs 5 to be killed. 4 is not going to suffice. And that's the key. I'm going to call, when I say killed by 5 iterations, I'm going to refer to that as these as bullets. So you need 5 bullets to kill v5. 4 is not going to do. So n4 mod n3. N4 is this 10-dimensional space, and N3 is this 9-dimensional space. So the quotient is going to be 1-dimensional, and it will be, and a basis is going to be V4 bar, so the equivalence class of V4. V4 needs 4 bullets. You can't get it done with 3. Similarly, N3 mod N2. So N3 mod N2. And 3, these are the guys that need 3 bullets to be killed. These won't do. These 9 vectors they span a 9-dimensional subspace. And N3 mod N2, N2 is a 7-dimensional subspace. This is 2-dimensional. And a basis for this is going to be V3 bar and W3 bar. So once again, V3 and W3, you can't kill them with just 2 bullets. 2 bullets gets you to V1 and to W1 respectively. And then similarly, we can do N2 mod N1. So N2 is the set of all, or the space spanned by these 7, and N1 is spanned by these 4. So the basis of this is going to be V2 bar, W2 bar, and X2 bar. And finally, N1 mod N0. N0 is just the 0 vector. N1 mod N0 is going to be isomorphic to N1, and here's a basis right there. And if you want to put bars over here, as we're modding out by 0, you don't really have to. I guess it technically maybe we should do that. Okay, so this map A minus lambda I is simple. It just A minus lambda I sends V5 to V4. So all this is saying is that it's going to send V5 bar, this equivalence class, to V4 bar. And when I say it's well defined, that means if you take two things, if you take x, say two things that are equivalent, x and x prime mod, and so two things that are the same in the quotient are equivalent mod n4, which means that x equals x prime plus z, where z is in n4, which means that z gets killed by 4 iterations of A minus lambda I. So if you apply A minus lambda I to x, then that's A minus lambda I times x prime plus A minus lambda I times z. So this thing, now we've already taken 1 bullet in each of these, so this thing here, A minus lambda I, this thing here lives in N4. This thing here only needs 4 bullets left to be killed, and this thing here is going to be in N3. So we apply A minus lambda I to things. Now really we should apply it to equivalence classes. Here I'm showing you individual elements, and I'll let you finish the proof yourself. But if two things differ by something in N4, then their image is going to differ by something in N3. And that's why it's well defined. And show its objective, I'll let you prove that as well. I won't say too much about that. That should be straightforward. So in other words, if you start with A minus lambda I, or if you start with the V5 bar, you apply A minus lambda I, you get V4. And this is the basis because the space is one-dimensional. So you apply A minus lambda I again, you get V3. And now this is 2-dimensional. This is not a basis. So you have to extend this to a basis. And in doing so, you get another element. Let's call that W3 bar. Now, you apply A minus lambda I again. Now you got a 2-dimensional vector space. V3 bar goes to V2 bar. W3 bar goes to W2 bar. This is 1-to-1. So the fact that this is 1-to-1 really confirms what I said earlier about how you're never going to have these things crossing. So you're never going to have V3 and W3, two different things going to V2. Well, you can, but they're going to be the same mod NJ. So any two things in here that map to V2 are going to be the same mod N2, which is mod something in here. Their difference is killed by fewer numbers of A minus lambda I. So V3 bar, W3 bar gets mapped to V2, W2 bar. This is injective, so this is a 2-dimensional, the image is 2-dimensional. The space is 3-dimensional because we are growing. And so we can extend that to a basis of the entire space by adding x2. And now, once again, we apply A minus lambda I one more time. You know what? I will add this V1, W1, X1. So we apply this. We get the image is 3-dimensional. But hey, look, the space itself is 4-dimensional. So we have to extend this to a basis, say y1. And this is how we are going to prove that there is a basis of generalized eigenvectors. We will always start out with this nd mod nd minus 1, and we will apply a minus lambda I, use the fact that it's injective, say, well, that's linearly independent, and now extend the basis and keep going. And that's basically going to work. So this is the lemma. I want you to, I've given you a hint for how to do this. I want you to prove this on your own, but I want you to really understand what it means. It's not this technical notational thing. It really is saying that these chains do exist, and that as we move to the right, we might have these new shorter chains appearing over time. Okay, so as you can tell, this is the start of the proof that we're not that far away from proving that X is going to have a basis of generalized eigenvectors, and that will lead us to the Jordan canonical form, and showing that two matrices or two linear maps are similar if and only if they have the same Jordan canonical form. So we are close to getting this stuff done. It will be finished over the next few lectures. Stick around.